So we talked about kind of different reasons why some locations are warm, some locations are cold. Also, it's kind of an assortment. So worldwide, then we kind of apply those things. So for instance, worldwide, you're going to see a map here. In general, it's warmest near the equator, coolest near the poles. But you're also going to kind of see the effect of like inland or continental locations kind of having less of a moderating effect of the oceans. So they're going to have more of temperature swings. Okay, so then the other thing you're going to see is that here in a minute, when we look at the temperatures of worldwide, that locations that are maritime locations near a cold ocean current are cooler, near a warm ocean current are warmer. So actually you can kind of see that on this next figure from your textbook. Okay, so the top one is January, the bottom one is July. So if we pick on January a little bit, let's see, yeah, these are in degree, they have them both in degrees Celsius and degrees Fahrenheit. So what would you call these? Starts with the letter I, like one earlier slide today, an isotherm. An isotherm, exactly. So, you know, in January, probably taking climate data, 30 years worth of data, these locations generally are at 70 degrees Fahrenheit. 60, 50, okay, you get the idea. So those are isotherms, exactly. Isotherms or isobars. So let's see. It kind of looks like, do you see, like I see kind of this little bit of a dip down here? And we kind of have a dip in, I guess I would call it kind of a dip in the cold temperatures over land masses. Okay? And that's because these ocean locations have the moderating effect of the oceans. So that makes sense. The hot spots looks like it's red, maybe. Kind of, does this look like a hot spot? Kind of here. It's not right at the equator, because the equator is here, but it's close. All right, so keep that in mind. That was in January. So if we look at the well, first off, can you see it? It's like a little bit south of the equator. Look at the hot spot in July. Not so surprising. Now that hot spot, ooh, we've got even more of a hot spot. That hot spot goes up in July. So later on in this course, we're going to kind of talk about that hot spot. I'll give it a name. I'll call it the ITCZ. That region, that hot spot, it's called the Intertropical Convergence Zone. So basically the hot spot kind of migrates north in July and south in January. Cool. Let's see if we can see one last thing. Let's pick on North America. I can't really see if I look at our west coast and our east coast. So I guess let's look in July. Let's see. Does this look warmer? Yeah. Yep. And does this look cooler? Right. Over here, this would be our Gulf current. And this over here, we said was, what's the name of that low current? Remember? The one coming down? I can't remember. But it's a cold current. You can kind of see it there. All right. Very good. Okay, now this map then actually looks at throughout the year, so it's annual. But notice it's the ranges. If you were to look at a climatogram, what would be kind of the dip down from the cold time of the year and the warm time of the year? So we said we saw kind of the smallest range around the equator. And again, these are, they're not really isotherms, but they're in degrees Celsius and degrees Fahrenheit. what the temperature difference is. So near the equator, there's not much of a temperature difference. But, oh my gosh, look at this. If you were up there in Canada, okay, if you compare your summer temperature and your winter temperature, you're looking at 90 degrees difference. That is crazy. What kind of difference do you think we are? Maybe maybe here-ish, just kind of picking one. Our swing throughout the year. So notice where you see your crazy swings. To me, you see your crazy swings, well, maybe not there as much, but you see your crazy swings kind of where there's land. So this again reinforces that if you're on land, if you don't have your ocean to kind of buffer your temperature change, you're going to have some temperature swings. All right. Let's talk about throughout the course of a day. And again, you already know a lot of this stuff. Okay. We talked about solar angle. We said that actually the higher the sun is up in the sky, we call that a bigger angle. Okay. And the larger the angle, the less beam spreading and the less beam depletion you get. Okay, small angle like at the sunrise, okay, you got a lot of beam spreading and beam depletion going on. Okay, noon, less amount, okay, and sunset. So throughout the day, you know, we definitely have that whole angle thing changing. The other phenomenon that happens throughout the day, especially on a sunny day, I guess I would say, if clouds aren't in the way, is the geosphere. The Earth's surface is soaking up energy, okay? And then I like to kind of think of it is actually releasing that energy right away, but to me also it's kind of delayed when it turns around nighttime away from the sun. It's really, you know, that's all we got for heat, okay? So kind of keep that re-radiation in mind. So from sunrise to noon, the angle's getting larger, and from noon to sunset, the angle's getting smaller. Actually, you're going to kind of see that here in a curve. Go figure, another figure. Okay. So this lag of maximum means lag of maximum daily temperature. So one of the things you may already know is that the hottest time of day is maybe 2-3 p.m., and actually, that's kind of what your textbook would say. And the reason for that lag actually is because the Earth is kind of oozing out its energy back. And it takes a little while to kind of catch up. Okay, so the warmest temperature is going to be about 2-3 p.m. And like the slide says, the coldest temperature is right when you're, like if you go camping, like right when you have to get up to go to the bathroom or something. It's just the coldest ever. So anyway, sunrise are your coldest temperatures. Okay. And of course, if clouds are there, kind of all bets are off, or changes a little bit. So this is a temperature profile of, again, in Peoria, Illinois. Okay. So basically, it's over several days, 5/19, 5/20, 5/21, etc. And I'm going to show you a device here in a minute that's on, but basically they take a piece of paper and it's on this slow-moving barrel, and this pin goes up and down. So this barrel turns and the pin goes up and down saying what the temperature is. So it's military time, so if you were to pick any of these peaks, okay, so this peak is, let's see, 12 is noon and 16 is like 4 o'clock. Okay. So it's about 2 p.m. there. Here it's about noon. Here it's about 2 p.m. Here it's about maybe 3 or 4 p.m. Okay. Here it's about maybe 2. And I like what your author said, because one of the things I had totally blown off is what affects temperature. I mentioned it before, but basically are these air masses that we're going to talk about later. A chunk of air that gets really cold over like Canada and moves down, or a chunk of air that gets nice and toasty over something south of us and moves up. Okay, so, and actually a cold air mass moved in, you know, right about there to kind of change the temperature. So this slide is basically kind of what you saw a minute ago. You know, when are your coldest temperatures? Oh, about sunrise. When is your warmest temperatures? Let's see, noon. So this would be about, this is showing at about 3 p.m. And then this up above it actually kind of says why that is. So this is actually your lag of maximum. This is your lag. What a weird name. A lag, of course, is kind of behind, and maximum here is maximum temperature. Now, this down here, this right there, kind of that red hump there, is actually kind of showing you the incoming. Okay, that's the solar radiation. You're getting most solar radiation at noon. Okay, but our temperatures are affected by our re-radiation, and our re-radiation is this purple down here. So the re-radiation is a little bit behind. All right. So here we have water in its, I'll put S for solid state, and here we have water actually, usually, well, when you see ground fog like that, whenever you see fog, water is either a liquid or a solid. Okay? Or I should say whenever you see a cloud, either water's not a vapor, it's either liquid or a solid. So I'm guessing liquid for that. Although, have you ever seen like ice fog? No. Yeah. Yeah. It can not be bad. It can be bad. Okay, so in order to get either solidification or liquefaction, you guys would tell me you need to cool it down, right? If you want to get vapor to go into a liquid or vapor to go into solid, you got to cool it down. And when the temperature's coolest, near dawn. So oftentimes we'll see that form overnight or near dawn. All right. So what about what kind of temperature swings do we see during the course of a day? To me, this is just kind of rehashing what we talked about. Higher latitudes. Now, if you're like me, I have to concentrate on what that word says, because I swear I see altitude, but it's really latitude. So the higher latitudes, we're talking about closer to the poles, okay? They actually, the sun won't get as high in the sky, okay? So as it turns out, their temperature range is less over a given period, over a given day. But now, didn't we see that, like, if you go towards the poles, their annual temperature range is great, but their daily temperature range is small. Okay. Daily temperature range for a windward maritime location. So what that looks like is, if this is North America here, oh my gosh, that's awful. That's my Florida. That is so bad. My Canada's up here, USA here. Then we have our mountains here. So what that is saying, when it says a windward maritime location, that was, I don't know, can't remember, was that Spokane or something like that? That's something on the coast, you know, Pacific Ocean. And so actually that would have a smaller temperature range because of the ocean. And it's just stuff we've been talking about throughout the day. We already talked about if you have clouds present, clouds are going to basically make your range smaller, because clouds will make your nights warmer and your daytimes cooler. Yep. What else do we have? So here's another one for you. Do you guys remember when we talked about stuff in the atmosphere? Water vapor can kind of take the sting out of solar radiation. The water vapor can act as a greenhouse gas, and it can interact with incoming radiation from the sun too. So actually water vapor can kind of give a little bit of high humidity. That's what we're talking about here. When water vapor is humidity. High humidity can actually kind of dampen your range a little bit, your daily temperature range. So this semester, I decided to include something on this. This is like one of your little boxes in your textbook that says kind of think about it sort of thing. The urban island heat effect, and you've probably run into this before. The cities are warmer than the country. That's just it, the urban island heat effect. And it's kind of shown here with DC, Washington, DC. These are degrees Celsius in, I think, December. So you can kind of see the bullseye where it's hottest. I'll put hottest here. And then each of the isotherms kind of get cooler and cooler as you get away from the center of the city. One of the things is that concrete. You know, we talked about kind of specific heat is a what we call a thermal property of water. Water has a high specific heat. There is another kind of thermal property in general, and it's just concrete is just great at sucking up energy and holding it too, kind of like water. Another thing is plants. In general, not all cities, but I think sometimes cities try to kind of, maybe it's an urban sort of effort where they try to make it green. But the more green that cities can make it, the better it is. Because actually plants are good in cooling. Plants actually add an extra source of evaporation. You're like, how do plants do evaporation? Well, plants actually have liquid water that actually evaporates as part of their process. Okay, so since they have concrete and they lack plants, they definitely just have an overall warming effect. And sometimes you'll hear meteorologists talk about this urban island heat effect. Okay, well that's a good place to pause, to stop, and we'll take a break.